I'm Dr. S. Kalaivani, Assistant Professor of Physics, Erode Arts and Science College. Today I talk about elementary particles. The elementary particles contains introduction, classification, particles and antiparticles, and particles instability and conservation laws. This slide is presented by introduction of elementary particles. By the year 1932, only three elementary particles, namely electron, proton, and photon, were known. The discovery of neutron by Chadwick in 1932 raised the number to 4. These elementary particles are the building blocks of matter, and the characteristics is defined by the properties such as rest mass. The elementary particles discovered so far from a long list of around 200. This slide shows the chart of elementary particles. So first the elementary particles are characterized by baryons, leptons, mesons and antiparticles. Baryons belongs to nucleons and hyperons. Nucleons can be characterized by the two ways. One is proton and another one is neutron. And as well as hyperons is also characterized by lambda, sigma and omega. So here also leptons is as divided into four groups: electrons, photons, neutrons and muons. And mesons is also characterized by the three ways: pion, kaon and eta. This slide shows the symbol of elementary particles. This slide shows now elementary particle symbol, charge and spin and rest mass of proton, neutron, lambda, sigma, psi and omega particles. Let's see first baryons. So baryons is otherwise called as heavy particles. So first protons and particles heavier than proton from their group. Proton and neutron are called nucleons and the rest mass is called hyperons. Every baryons has an antiparticle. It is a number is called baryon number. +1 is assigned for a baryon and a number -1 is assigned for an antibaryons. Then in any closed system interaction or decay, the baryon number does not change. So this is the law of conservation of baryon. Source hyperons. So hyperons is a decay of the order of 10 power minus 10 seconds. Mass value intermediate between neutron and deuteron. The decay time is very much greater than the time of their formation, 10 power minus 3 second. Kaons strange particles is discovered by Gell-Mann and Nishima. Then hyperons is classified into four types, that is lambda, sigma, psi and omega. This slide shows about leptons. So it contains electrons, photons, neutrino and muon. All these elementary particles have masses smaller than that of a pion. So next electron. So first discovered by the particle is electron. So negative charge and a stable particle and an electrostatic field existed between two electrons. Now this slide shows photon and neutrino. So first I tell about photon. Photon has a no charge and no rest mass. It has energy given by the Planck's equations, that is E equal to h nu. So here H is a Planck's constant and E is the energy, and it has an equivalent mass given by the Einstein's equation, so that is E equal to mc square. So next neutrino. Neutrino is discovered by the spectra and radioactivity, beta radio spectra. So by the year 1956, it has no charge and rest mass is 0. It travels with the speed of light. It exists in two forms, one associated with the electron and the other with the muon. Source about muon. So muon is similar to the electron. It expert that its mass is about 200 times than that of electron. It decays very quickly with a half-life of 2.2 microseconds into one electron and 2 neutrinos. So it is a negatively charged and has a spin of 1/2. It was first discovered during the study of cosmic rays. So next slide shows that about a meson. So masses are between those of leptons and baryons. It is a unstable particles. They decay into lighter mesons or leptons when have either positive or negative or zero charge. The mesons include the pion, kaon, and eta particles. Slide shows that about a pion. So pion has a mass equal to 273 times. So this slide shows about particles and antiparticles. So there is particles electrons and antiparticle is positron. So it has the same mass and the same spin but opposite charge. They annihilate each other with the emission of photons. The existence of an antiparticles for each for the electron was actually predicted by Dirac because of symmetry of the equations of the relativistic quantum theory of the electron. Positron was discovered by the Anderson in the year 1932. This slide shows the proton and antiproton. So by the Dirac theory, anticipating the positron would be interpreted as implying a particle identical to the proton except for a negative charge. Antiprotons were produced by the bombarding protons in the target with 16 giga electron volt protons. Proton plus proton gives proton plus proton plus proton plus antiproton. So antiprotons interact strongly with matter and annihilate with the protons. Proton plus antiproton gives pion plus pion minus plus pion plus pion minus plus zero charge of pion. Neutron and antineutron. This slide goes to explain. So it discovered in the year 1956 by Koch, Lamberton and Wenzel. The nature of antineutron is not very well known. Both have zero charge and the same mass. Antineutron is quickly annihilated either by proton or neutron. So usually with a production of several pions. So it is an antineutron is not annihilated by a nucleon. It decays by the reactions. Antineutron gives antiproton plus beta positive plus neutrino. This slide goes to explain the continuity of neutrino and antineutrino. It was a charge 0 and a spin 1 by 2, 0 rest mass and a magnetic moment smaller than 10 power minus 8 both magneton and nearly 0. Finite energy momentum and travels with the speed of light. It does not cause ionization on passing through matter. The spin of neutrino is opposite in direction to the direction of its motion. The spin of antineutrino is the same direction and its direction of motion. The neutrino moves through space in a matter of left-handed screw. So while the antineutrino does so the manner of right-handed screw. Slides tell about neutrinos emitted in beta decay have a negative helicity. They are longitudinally polarized with a spin axis and parallel to the direction of travel. So here, because of its lack of charge and magnetic moment, a neutrino has essentially no interaction with matter. So matter is also about totally transparent to neutrinos. This slide shows about conservation laws. The conservation laws is conservation of parity, conservation of charge conjugation symmetry, and time travel symmetry, and combined inversion of CPT. So conservation of parity is going to tell about parity relates to the symmetry of the wave function that is represented by the system. If the wave function is unchanged, then the system has a parity of +1. If changed, then the parity of the system has -1. During a reaction in which parity is conserved, the total parity number does not change. Prior to 1956, it was believed that all reactions in nature obeyed the law of conservation of parity. Indeed, parity conservation is found to hold true only in the strong and EM interaction. This slide shows about charge conjugate symmetry. It is the act of symmetry operations in which very particles in a system is replaced by its antiparticles. If the antisystem or antimatter counterpart exhibits the same physical phenomena, then charge parity is conserved. In fact, C is not conserved in a weak interaction. So this slide shows about a time reversal symmetry. Time parity T describes the behavior of a wave function when T is replaced by minus T. The symmetry operations corresponds to the conservation of time parity is time reversal. The direction of time is not significant, so that the reverse of any process that can occur is called the process of can occur. One form of K naught, that is neutral charge, can decay into pion plus or pion negative charge. The symmetry of phenomena under time reversal does not seem to be universal. The slide shows a combined inversion of CPT, that is, combined symmetry operations in which the antimatter mirror image of a system is run in reverse all allows a test of CPT invariance. The conservation of CPT means that for every process there is an antimatter mirror image counterpart that takes place in inverse. This particular symmetry seems to hold for all interactions, even though its component symmetries sometimes fail individually. Thank you.